for today. And I guess with the theme of we are all individuals, we have a talk here on individual cryptography by Stefan Zimbowski, Sebastian Faust, and Thomas Ligeray. And Thomas will give the talk.
Thank you so much for the introduction.
Yeah, I think you might want to move it closer to your.
Yeah. Do I need to turn?
Do you have a microphone?
Hello. Is it working? Yeah, it's working. So thank you so much for the introduction. And with this work, we are trying to initiate the study of individual cryptography. This is cryptography that is secure against distributed cryptography attacks that can be carried out using the multi-party computation protocols or trusted execution environments. So kind of our work stands in contrast to a broad set of works that tries to improve the efficiency and practicality of multi-party computation protocols, as we observe that they may be used spitefully. But let me start with motivating our work, showing how some examples of those multi-party computation attacks. So I will start with the account sharing problem. So let us imagine some online service that runs on subscription fees model. And maybe it's an online storage service. And usually the service provider would assume that every new user of the service would pay a separate subscription fee. But this is not often the case, as the users tend to lower the costs of the service, and maybe they share their credentials with some other users. For example, they could even share their credentials with some users that they have met on the internet and they do not fully trust them. So some solution for the service would be try to incentivize the users not to share their credentials. For example, by creating some threat that anyone with the access to the credentials can pose some harm to the account. For example, in this online storage case, one could delete all the files on the account. And this threat could work if the parties do not fully trust each other. But if we take into account the MPC attacks, this solution does not work. Why? Because these parties can collaborate together. They can emulate the knowledge of the secret information in a way that no one really knows the secret information. And having MPC in hand, they can control the access to the service. And no one is threatened that his files or her files would be deleted. And in our work, we try to protect against such attacks by showing a proof of individual knowledge. So it will be a protocol between a prover and the verifier. The verifier will run on the side of the service, and the verifier will be able to check whether some information is fully stored on a single machine and it's not divided between some parties. Now, the second example that I would like to mention is the example of partial reconstruction of shared secrets. So let us imagine we want to get some special secret sharing scheme that would allow some parties to secret share an information in a way that they can obtain any function of the information if only at least one of the parties has full information in the hand. And this scheme, for example, may be used to incentivize these users to recover the secret information only with some delay. And of course, any simple secret sharing scheme, like the additive secret sharing scheme, would not work here because the parties could again employ the MPC attack, and they can play together to get some function out of the secret without really knowing this secret. So in our work, we are proposing a scheme that is individual secret sharing scheme, and we are having this property that the parties are able to get the function of the secret only if at least one of the parties fully knows the secret, or when they perform really heavy computation on the secret. So now that we have some motivation of our work, I would like to give you some intuition behind the model that we provide in our work, and then provide the model from our work. So the overall goal is to design the algorithms which are easy to compute once someone has a full secret information needed to compute this algorithm, but they are hard to compute once this secret information is secret shared or divided between a set of parties. But can we find any function that is hard to compute in MPCs and it's easy to compute outside the MPCs? And we have to consider different techniques that the adversary may use. Of course, he can use the MPCs, the protocols with provable guarantees that would let the adversary to hide some secret among a set of parties, but they can use these trusted execution environments. The trusted execution environments, they are implemented usually in the CPUs, and they allow these parties to run in a trusted manner some part of code. And this way, they can be like pre-programmed to run similarly to the multi-party computation protocols. And how do we find functions which are hard to compute in MPC and TIS? For the MPC, it seems like the answer is easy, because simply the sequential computation of hashes is hard in the MPCs. For sure, it's much slower than in the CPUs. But is this enough for the trusted execution environments? It seems like no, because these trusted execution environments, they run in the CPUs themselves, and usually they are almost as fast as the CPU themselves. So we need to look for some other assumption. Maybe we can explore some limitations of the trusted executions, like the limit of the memory that these trusted execution have. But we decided on some other assumption, and we decided on the assumption of massive parallel computations. So we observed that on the market there are available devices like Bitcoin mining ASICs, which are specifically designed to run like billions of hashes in a unit of time, and they are extremely fast. They are much faster than the CPUs. Of course, that they are faster than the trusted execution environments, and they are even much faster than the GPUs that could be used to run the computation of hashes, because we may expect that the GPUs could also implement trusted execution environments in the future. And now, with this assumption of the massive parallel computations, we can leverage this fact that the hashes are computed much faster in the Bitcoin mining ASICs than any MPC or T technique. And we can try to build the model. And we start building our model with defining the distributed adversary. And the distributed adversary will be simply a set of sub-adversaries that try to hide the knowledge about the secret, about some secret together. And these adversaries, they could communicate, for example, via a single party with the other participants of the protocol, of some protocols, the honest participants, to model the fact that no one really knows whether he or she is talking to a single party or a set of parties. And now these parties could communicate in rounds. In each round, these parties could do some computations individually, and then they could share some partial information to the other parties. And this adversary, during the execution of a protocol or some algorithm, will talk to an MPC-Oracle, an oracle that will model how this hash function is computed in different environments. So the queries will be of type X and mode. X will be input to the hash compression function, and mode will model the different settings of computation. So with the mode slow, we will model how the H function is computed in the MPC setting. And this will be modeled by two facts. The first fact, this is slow setting. So we will have a bound on the number of queries that can be asked in this mode. And the second fact is that in this mode, the adversaries will be able to hide the input to the query. So the input of a query will not be revealed. And in a fast mode, using the fast mode, we will model how the function is computed in these Bitcoin mining ASICs. And we will have unbounded number of queries here, but the inputs will be revealed. So the parties will show that they have some knowledge about the input to the query. But how do we model the knowledge in our work? So we use the concept of extractors. We actually extend the concept of extractors to the distributed adversary. So during the execution of the protocol, the sub-adversaries are making queries to the oracle. And each sub-query creates an individual fast hash individual transcript of the queries to the oracle. But we will care only about the knowledge of the fast queries to the oracle. So we will care actually only about the knowledge of the fast, of the queries in the fast mode. And after a protocol is finished or an algorithm is finished, this knowledge, the fast hash transcript, will be given to the extractors that will make an attempt to extract the secret information from the individual fast hash transcripts of the sub-adversaries. And of course, these extractors will also have an access to the oracle themselves. Now that we have our model, I will try to show you how to build up some construction using our model. So I will try to show you our construction of proof of individual knowledge. So it's a protocol between a verifier and a prover. And at the end of the execution of the protocol, the verifier is supposed to say yes or no, whether he believes that some information is stored on a single machine by a prover. And now for completeness, we will consider a bounded verifier and a prover. So we will want to give a bound on the number of queries that verifier and approver can make to the oracle. With this fact, we model the fact that they are efficient. And we say that the protocol is complete when the bounded verifier and approver are able to finish the protocol with overwhelming probability. Now for security, we will consider a verifier talking to a distributed adversary. And now we will say that the protocol is sound, it's secure, whenever it can be finished with output yes, only after every execution of the protocol, full secret information needed to compute response to this protocol can be extracted from individual fast hash transcript of one of the parties. And of course, the goal will be here also to keep these extractors efficient and with low number of false positives, because the parties can always just make full queries, fake queries to fool the extractor, Now, how does our protocol work? So a verifier starts with choosing some random challenge and sending it over to the prover. And now prover has to do extensive amounts of computation. So he's asked to find kappa nonces such that the output of some function scratch starts with zeta zeros. And finally, the verifier is able to verify the correctness of the computation. So this protocol is simply similar to the Bitcoin proof of work, but there are two things. We are asking the prover to find kappa nonces, not only one. This is to lower the variance of the output of the protocol. And the second thing is we are using this some scratch function, not simply the hashing. Why do we use this scratch function? Actually, the popular hash functions, they process linearly long inputs. So, for example, they use the Merkle-Damgard scheme to compute to process the long inputs. So usually they define some basic building block, the compression function that is defined for fixed input length and fixed output length. And now, whenever they get some long input, they would start computation with computing the hash over the first part of the input, and then they would continue computing the hash using the second part of the input. So there's a threat of pre-computation attacks. We call it pre-computation attacks. So if we have a long secret, we can give the first part of the secret to one party, we can give the other part of the secret to the other party, and now the first party can start the computation using the first part of the secret. Then the partial result can be handed to the other party, and the other party can finish the computation, can obtain the output without really knowing the first part of the secret. So we have to protect against such attacks in our work. So what we do, we really carefully design this scratch procedure. So if we have this hash compression function, we have this challenge Z and the nonce W. First, we start with hashing this challenge and nonce, and then what we get our secret and we divide it into blocks of equal length. And now we process these blocks one by one, similarly to the Merkle-Damgard scheme. But what we do more to protect against the pre-computation attacks, we repeat this computation, we feed the output of the first column as the input of the next column of the computation. And when, again, to force the adversary to compute on a full secret, we ask him to do the computation again on all blocks of the secret. And we will repeat this process at least rho plus 1 times, where rho was the bound on the communication rounds that can happen between the parties. So in other words, if the adversary is forced to compute so many columns in a single scratch attempt, it means that at least one of these columns must be computed fully by a single party. So a few words about the security of the protocol. For completeness, we will say that for every nonce, we will need to do around 2 to zeta plus 1 scratch attempts to be able to finish the protocol with high probability, and we will have the kappa of these nonces, and then the verifier will just have to verify these kappa nonces. For soundness, we will show in our proofs that a large number of these columns have to be computed individually to be able to finish this protocol. And based on this fact, based on the fact that we have a large number of columns in the transcripts, we will be able to define efficient extractors that are extracting the secret information. Now, in this work, we kind of defined the concept of individual cryptography, and we strongly encourage you to look for applications and places where where the MPC or T attacks may be applied. What is more, we encourage both the engineering and the scientific communities to understand more which functions are MPC and T hard, and to understand, for example, if this concept of MPC hardness can be obtained without an access to the Bitcoin mining ASICs. Thank you.
Okay, we have time for a couple of questions if there are any in the audience.
Firstly, fantastic talk. I'm curious in the TEE case how if the performance of the TEE increases and gets closer to the performance of the Bitcoin miner, how that affects the probability that the protocol actually works out and is able to detect an adversary that's like trying to share secrets.
Of course, if the T's are as fast as the Bitcoin mining ASICs, then the security is broken. But still, I think it's a huge work to implement these T's even in the GPUs. And the Bitcoin mining ASICs, you know, they are using a lot of like hardware optimizations to run these computations faster. So it seems like maybe it's hard to implement T's in this setting.
That makes sense.
Of course, it seemed natural that looking at the memory heart functions, did you look at it a little bit and see issues with using them? Because it would seem natural, like a computer would be able to handle something that a trusted execution environment couldn't handle.
You know, for now, we just wanted to focus on this simple Oracle model, and that's why we skipped this memory limit assumption. But we think it's another way to explore the concept of individual cryptography. Yeah, so we don't have many insights right now, but it's a thing to explore.
Okay, let's thank the speaker again. And we'll just wait a couple of minutes until 5:35 before we start the next talk.
Test? Okay, cool. Thank you. Test? Test? It's green. Oh. Okay.
Okay, the suspense is over. The final talk of the session will be on random Oracle combiners. This is a joint work with Evgeny Dodis, Niels Ferguson, Peter Hall, and Christoph Petschak. And Peter will give the talk.
Or Eli. Eli will give the talk.
Okay, well, your name's not on the slide.
Yeah, sorry. But yeah, I'm Eli Golden.
So somebody is going to give the talk, and you can introduce yourself. Sorry.
Okay, yeah. So hey everyone, I'm Eli Golden, and this is joint work with all the authors listed before. I'm going to be talking about a new notion of hash function combiners that we refer to as random Oracle combiners. So I'm going to begin by talking about what are hash function combiners. And I'll motivate this with a short fictional example. So recently, your favorite tech company, Goggles, purchased a new cryptocurrency startup, Coin Company, and welcomed them into their fold. Coin Company loves to use their new proprietary hash function CoinHash, which they use for everything and they think is the most secure thing ever. But Goggles is a bit more traditional and only wants to use SHA-3. And so they're at an impasse. They both have different hash functions they want to use. If only there were some hash function that would make both of them happy. And this is where combiners come in. With a combiner, we can take SHA-3, CoinHash, plug them in the combiner, mash them together, and get a new hash function, CoinSHA, of which both companies will approve. So more generally, a combiner will take in two hash functions, H and G, and output a combined hash function C, which will be secure as long as one of H or G is secure. And I'll go later into various notions of security that you can define combiners for, but this is a fairly informal definition. Okay. And so how do we judge combiners? There are three main metrics that I like to consider. First of all, we can look at the output length of the combiner. Ideally, the combined hash function should have output length the same as the initial hash functions. We can also look at what security properties the combiner works for. Does it work for collision resistance or one-wayness or something like that? And finally, we can look at the efficiency of the combiner. How many times does the combiner call the initial hash function? Yeah. So now that we have some notion of what combiners are and how to evaluate them, I'll talk about prior work and bring us up to the state of the art. Note that for most concrete security properties, combiners are fairly easy to define. There's usually a simple combiner that works for any security property, or at least a concrete security property. For example, collision resistance, concatenation is a very good combiner. And there are other combiners for different security properties. Note that the combiners for the simple combiners, at least, for different security properties all look very different. And in particular, concatenation is not going to work for one-wayness or pseudo-randomness. And so this leaves us with the question, okay, is there some construction of a combiner that will work for all of these properties at once? This question was answered in the affirmative by Fischlin, Lehman, and Pietrok in 2008 and 2009, where they defined a new notion called a multi-property preserving combiner. And they constructed a combiner that works for collision resistance, pseudo-randomness, target collision resistance, max security, and one-wayness all at the same time. In terms of the other parameters for combiners, their output length is twice the output length of the initial hash functions. And in terms of efficiency, they call each underlying hash function 3 times. And these parameters, seem quite good until we notice that, sorry, this is not the latest version of my slides. Until we notice that hash function outputs are often sent over the internet very frequently. And so the output length is really, really important for practical efficiency. And so having an output length twice as long as the initial hash functions can be prohibitively expensive. And so we would really want to get a multi-property preserving combiner with output length n, the same as the original hash functions. And even just limiting our scope a little bit, we can ask the question, even just for collision resistance, can we get a combiner with output length n? And unfortunately, there is an impossibility result due to Bonnet, Boyan, and Pietrok that showed that any black box combiner for collision resistance must have output length 2n, or twice the length of the initial hash functions. And note that this is actually the same output length that the concatenation combiner gives. So really what this impossibility result says is that concatenation is the best possible combiner for collision resistance. But in practice, we really want combiners with output length shorter than 2n. This is kind of prohibitively expensive. So we can ask, okay, is there any way that we can get around the concatenation barrier, perhaps with some clever modeling? And the answer to this, at least a partial answer, as known so far, is yes. In 2013, Mittelbach introduced this paper, Cryptophia's short combiner, with a follow-up correction by Minick and Pernille in 2014, that showed how to get around the concatenation barrier by clever modeling. In particular, the key observation that they make is that if we assume that the hash function is a random oracle, this is a much stronger assumption than collision resistance. And so perhaps we can get a better combiner by making the stronger assumption. Note that since we're modeling the honest hash function as a random oracle, this leaves us a question: how do we model the insecure hash function G? Because for normal combiners, G is going to be some adversarial circuit. But if the honest hash function is a random oracle, then an adversarial circuit is going to be independent of the random oracle. And it's not really going to capture the notion that the adversarial hash function can be designed with the honest hash function in mind. And so as a natural approach, the Cryptophia paper models the adversarial hash function as an oracle circuit with oracle access to the random oracles and bounded number of oracle queries. Okay. And so the model that the Cryptophia paper works in is that a combiner will be an oracle circuit with two oracles, such that as long as one of the oracles is a random oracle and the other is an adversarial hash function, the combiner should satisfy some number of concrete security properties, and hopefully simultaneously. And so the Cryptophia paper actually manages to construct such a combiner and gets the output length to be the same as the original, which is exactly what we want. And we can also look at the other properties, the other metrics that we judge combiners by. In terms of security properties, it takes a random oracle and turns it into something that satisfies one-wayness, collision resistance, max security, and pseudorandomness. Note that this is great, but it is a little bit of a degradation of security. We're taking something stronger and mapping it to something weaker. So we can ask, okay, is this good enough for practice? In terms of efficiency, the number of calls is much more than for multi-property preserving combiners, and actually depends on the input length of the hash function. And so we can ask, okay, is this efficiency optimal for combiners with output length then? And in this work, we show that the answer to both of these questions is no, it's not good enough and it's not optimal. And for now, I'm going to focus on the security properties. Okay. In particular, we can ask the question, are concrete security properties enough? And note that there are many, many different constructions that use hash functions that have no reduction to any concrete security property, but have security proven heuristically secure in the random oracle. And so I'd like to make the argument that for practice, we really want hash functions that are random oracles, not just something, or that are heuristically a random oracle at least, not just something that satisfies collision resistance or one-wayness. And so this idea led us to define the notion of random oracle combiners. And so a random oracle combiner, as we define it, is just a combiner as in the Cryptophia model, but instead of requiring some specific properties on the combined hash function, we require that the combined hash function is a random oracle. Note, what do I mean by is a random oracle? This is a little bit of a question, because this combiner is not literally going to be a random function. But luckily, there is a nice framework that deals with this, known as the indifferentiability framework. The indifferentiability framework really models what it means for some construction to be a random oracle in a practical sense. I'm not going to formally define what indifferentiability means, but the key thing to note about it is it has a very versatile composition theorem for single-stage security games. That is, if G is any single-stage security game, which is secure in the random oracle model, and C is a construction, which is indifferentiable from a random oracle, then G is going to be secure when the random oracle is replaced with the construction. I'm not going to define what I mean by single-stage security games, but roughly you can think of this as being security games with only a single adversary. And so to summarize, a random oracle combiner is just going to be a combiner in the Cryptophia model where the combined output is indifferentiable from a random oracle. Okay, this is the more formal definition. Unfortunately, we proved the theorem. Random oracle combiners do not exist, at least as stated before. And the intuition for this is fairly simple. We know that the adversarial hash function, g to the h, can evaluate the combiner on 0. And so using some sort of rejection sampling, g to the h can bias the combiner evaluated on 0. But note that the key idea here is that we crucially rely on the fact that the adversarial hash function can evaluate the combiner. And so what this really means is that no deterministic random oracle combiners don't exist. And so we can get around this impossibility result by simply allowing the random oracle combiner to be salted. And in fact, it's important to note here that the random oracle combiner with the salt is simply going to be a family of hash functions for which the key for the family of hash functions will not be given to G, but will be given to the adversary in the indifferentiability. Okay, and so now that I've defined what random oracle combiners are, we actually managed to construct one. And so I'll go through the construction now. The construction is fairly simple. What we will do is we will split the salt up into 2 parts. So the salt Z will be split into 2 parts, Z1 and Z2. And the combiner evaluated on M, the combiner C evaluated on M, will simply be H of M comma Z1, XORed with G of M comma Z2. That is, we individually salt the 2 hash functions and XOR their outputs. Note that the salt that we will use for these hash functions will be security bits longer than the length of the input. And so our main theorem of the paper is that C, as described here, is a random oracle combiner. And so the main claim, the main intuition behind this proof is that we were going to show that for any input M, G on M comma Z2 will never query H on anything comma Z1. Which means that if we define some H prime to be H of M comma Z1, H prime is going to be a random oracle, which is entirely independent of G on anything comma Z2. And intuitively then, our combiner applied to N is just going to be a random oracle on M, XORed with a completely independent function, which is trivially then indifferentiable from a random oracle. No, I'm sweeping a number of details under the rug here, but this really is the heart of the argument. And so all that really remains to be shown is this main claim, which is that for all M, G of M comma Z2 will never call H on anything comma Z1. And we can show this really just by looking at the table of queries made by G. Note that on any input, if we look at the table of all queries made by G on any input M, what is the size of this table? Well, it's simply a bound on the number of queries made by G times the number of possible messages, which is then T times 2 to the M, where T is a bound on the number of queries made by G. So then the probability that anything comma Z1 is queried by G of anything comma Z2 is just the probability that Z1 appears in this table somewhere. And so by union bound, we can upper bound this by the size of the table over the number of possible values for Z1. And since Z1 is security parameter bits larger than the length of the input message, this is upper bounded by the number of queries made by G over 2 to the security parameter, which should be negligible. And so this actually is the end of the proof. So our construction C is in fact a random oracle combiner. And so now we can look at our random oracle combiner under the 3 metrics we care about. The output length, same as the original hash functions, same as Cryptophia, which is exactly what we want. In terms of security properties, we're a random oracle combiner. That is, we're taking a random oracle and mapping it to a random oracle. And in terms of efficiency, we're only making one call to the underlying hash functions. And so kind of in all of these senses, we're a strict improvement over the Cryptophia result. And in theory, this is great. But we might be asking the question, OK, what happens if we plug in real-world hash functions into our construction? And so what do I mean by real-world hash functions? Well, in practice, most hash functions are going to start with some compression function, taking an input to a slightly smaller input, and then apply some transformation to get a hash function taking a large input to a small input. And the most famous of these transformations is the Merkle-Domgaard transform, which essentially operates by composing the compression function with itself and introducing the input block by block. Okay. And we also know through Caron, Dodis, Molyneux, and Bernia that the Merkle-Domgard transform is actually going to preserve indifferentiability. That is, if we are given a random oracle H, the Merkle-Domgard transform applied to H will be indifferentiable from a random oracle. And we also know that indifferentiability has some composition limit. And so our first attempt to prove this will be to simply say, okay, we have that C is secure, and we have that H star is going to be indifferentiable from a random oracle. I'm sorry, the slides are a little bit outdated, so this is not corresponding exactly to what's there. And so we should be able to get that our construction composed with Merkle-Domgard is secure. But note that the indifferentiability composition lemma is only going to hold for single stage games, unfortunately. And so we might ask the question, okay, is our game single stage? And it turns out that, unfortunately, it is not a single stage game. And so I'm not going to go into details about why it's not single stage. But I just want to say that in our paper, we actually give a concrete attack against this composition lemma. We give a concrete construction of a combiner, which should be secure, assuming that the differentiability composition lemma holds, but which is not actually secure in our model. So unfortunately, composition does not work to show that our combiner instantiated with Merkle-Domgard is secure. But we might ask whether we can prove this directly instead. That is, if we have H and G two compression functions, can we directly show that our combiner instantiated with the Merkle-Domgard of H and G is indifferentiable from a random oracle? And we leave this as an open question, but we conjecture that it is true. And we were unable to prove this in our work. And this is a pretty hard question. So instead, we decided to ask a somewhat simpler question. Okay, can we actually just prove this directly in the Cryptophia model? That is, if H star and G star are two Merkle-Domgard hash functions, can we show that our combiner instantiated with H star and G star satisfies collision resistance? And we are able to do this. We did actually succeed in proving this theorem. So yes, our combiner instantiated with Merkle-Domgard hash functions satisfies collision resistance. And so this is the informal result. And so what was the intuition of this proof? So this is actually, I would consider the technical heart of the paper. It's a lot more subtle than the other proof, of which I can run through. But I'll give some kind of key intuitions. The key intuition is that we will use any collision adversary against the collision resistance game to compress Z1, that is the salt for the actual random oracle. And the key idea, the key property that we will use for Merkle-Domgard hash functions is that if you apply a Merkle-Domgard hash function to any input x, then any process which computes H star of x must query each round of Merkle-Domgard. And so therefore, if we are able to find a collision, C of m equals C of m prime, then either G star of m comma Z2 or G star of m prime comma Z2 will have to query H star of m comma Z1. And so we'll know Z1. And then what this means is that we can compress Z1 just by using m along with a list of the relevant queries made by G star. And so for our parameter regime, we show that this is impossible. And so therefore, our protocol must be collision resistant. I'm going to end on 3 open questions. The first is the open question from a few slides ago, which is, does our combiner actually satisfy indifferentiability for Merkle-Domgard hash functions? The second question is a little bit more technical. Is there any combiner which does compose nicely with this indifferentiability composition lemma? Is there some other construction that we can do for which we can prove some notion of composition lemma for maybe some restricted form of indifferentiability? And my final question is about the amount of randomness used by our combiner. Note that we required that the salt was supposed to be have length of the same length as the input plus an extra security parameter bits, but this is actually quite a lot. We might wonder if there's some construction that only uses security parameter bits for the salt. Yeah, and thank you. End of my talk.
Okay, we do have time for questions for Eli Golden. If anyone would like to ask a question, yeah, go ahead.
So thank you for the talk. Just a quick question about the deterministic case for combiners. So you gave this attack that shows that you can induce some bias, but do you think there's some meaningful notion that could be achieved in the deterministic case that is more general to the individual properties, like some biasable random oracle to some limited extent or something like that?
So actually, the Cryptophia paper also is salted. I kind of avoided that. So perhaps we could get some sort of Cryptophia result, or for some specific properties. I'm not sure if there's anything you could get that's more general than that. I'd have to think about it a little bit, but I'm not even sure that the Cryptophia result is possible in this model.
I mean, on the same line, is it meaningful to think of G that doesn't depend on H, or does that trivialize the question?
That trivializes the question. If G does not depend on H, then XOR just with no fault or anything is very easy to show as a good combiner.
Okay.
So I was going to point out that basically that point that it seemed like you start out by saying, okay, we've got a function and then random oracle, and that's automatically independent. And then you kind of said, well, we'll give it access to the random oracle, but then we'll just add an assault. And it seemed like it kind of somehow that seemed almost like cheating, which maybe that.
So it is kind of, I guess, the issue here is that the salt really needs to be long for this construction to work. And in fact, if the salt is only the length of the input, then this construction is kind of broken. I would say that maybe our main construction is relatively simple. There are a lot of open questions to kind of continue answering. But it doesn't, even just having lambda bits of randomness, it's not clear how a salt will get you all the way there.
And I guess I also was wondering, you made the comment about Merkle-Damgard being indifferentiable from a random oracle. Is there some extra step there, like fixed length or something? Because otherwise it's not true.
Yeah. So in our paper, we're operating in fixed length model, but yes, there's some other variants that you could also do. Yeah.
Just an understanding question. The salt, is this more like an IV, which I sample once for the combiner and then I keep it, or per message they get something like target collision resistance?
It's like an IV. It's sampled once per the combiner, and then you can just use the combiner forever.
Thank you for the talk. I was wondering if you looked into trade-offs where you would call the underlying functions more times, and if that lets you, for example, shrink the salt if you call the underlying functions on, say, only security bits at a time.
We thought about this. We were not able to get anywhere with it. The Cryptophia combiner actually does do something like that. The salt that they use is a lot shorter than ours. But I'm not sure how to get to random oracle combiners using this method.
Thank you. All right, so why don't we thank Eli again? And that concludes the session. I think dinner is in about half an hour from now.